Good. So welcome to our LibreHub seminar for this week. I'm thrilled to announce that we're welcoming Dr. Lei Tian. He's an assistant professor in Boston University, where he's in the Department of Electrical and Computer Engineering and the Department of Biomedical Engineering, and he directs the Computational Imaging Systems Lab. He received his PhD and Master of Science from MIT in 2013. And he was a postdoc at UC Berkeley until 2016. His research focuses on computational imaging and microscopy, neurophotonics, imaging in complex media, and deep learning for biomedical microscopy. Dr. Tian's awards include NSF Career Award and also 2021 Boston University College of Engineering Early Career Excellence in Research Award, and also another award from the same university, Catalyst Award, and also 2018 SPAE Fumio Okano Best 3D Paper Prize. I hope I pronounced that correctly. So join me in welcoming Dr. Lei Tian. He will tell us about his research.
All right, let me share my screen.
Okay. We can see the presentation. Okay.
All right. Sounds good. So let me get started. Thank you again for the kind invitation, particularly to Vicente, to introduce me to this great audience. So I'm going to talk about, in general, computational microscopy technique developed in my group. So the theme is, we would like to build low-cost, simple optics, but can be augmented by advanced algorithms for advanced biomedical microscopy applications and neuroimaging applications. So I guess just to speak to this particular audience, the two techniques I'm going to talk about, the common theme is that they're quite simple and we put everything online, so they're open access, and including both how you build it and the algorithms. And also I will show up some examples that may be familiar to this audience, how people have been reproduced these results. Okay. So before I get started the real business, I'm just do a quick introduction of my group. So I lead the Computational Imaging Systems Lab at Boston University. So in general, we work on optical hardwares, computational modelings, and algorithms, and for various different scientific and biomedical applications. So just to talk a little bit about how do I think about computational imaging. So in general, what you're going to see in the two examples I'm going to talk about involves this general pipeline. So you have some kind of optical signal that carries underlying interesting biological and neurological quantity of interest, or interesting, denoted by X. So the imaging systems, after we build it, we need to model it. So I'm going to talk about some modeling effort we do, denoted by A. So then we take some measurement. So once we have that, in general, for computational imaging, the idea is that we want to leverage this measurement, denoted by Y, and solve some kind of inverse problems to look for the underlying X. So because of this, you can think about, we work with two diverse space that are synergistic. One is in the hardware/acquisition designs. So the other is computation. Okay? So we have these two sides we can leverage. So in addition, for computations, because of these days, there are a lot of different techniques have been innovated. So I'm going to talk about two kinds of computational methods. One is using physical models, and the other is using deep learning. So in general, a lot of my lab's work is looking for the synergies between the hardware designs, acquisition designs, and computations, so that we can push the imaging capability. So around these themes, we work on various different things: computational face imaging, neuroimaging, imaging in complex medium, and various other things using deep learning. So today I'm going to focus on the top two, starting with this computational face imaging. So like I said, the setup is very simple. So let me walk you through this. So basically we have a standard microscope. So this microscope can be anything. So this is just set up in my lab. But in general, if you look into this topic of LED array microscopy, it had been quite a few groups working on this topic, initially from Chang-Hui Young's group in Caltech, and later I did extensive work during a postdoc with Laura Waller in UC Berkeley. So then we reproduced in my group. So the principle is the same. So we have a standard microscope, then we replace the standard light source with an LED array. So this LED array can be programmed to have any patterns. So there's two examples. One is turning on one LED or a circular pattern. Okay? So the idea is that by playing with these illuminations, you can develop various different imaging modalities. So among the communities, we have been working on various different modalities. So these are the two things have been worked on in my group. One is for 3D, so phase tomography. The other is for wide field of view, high resolution phase microscopy. So I'm going to focus on the first one. So this 3D phase microscopy, just to give you the idea, the kind of things we can do with this kind of hardware. Okay, so how do we do this? So now we're getting into a little bit of details. So the problem we solve for this type of problems is known as intensity diffraction tomography. So the data set is something like this movie is showing. So essentially we scan through different illumination angles and take the corresponding intensity images. Our goal is to recover the quantitative phase information of the 3D object. And this phase information is useful for characterizing typically transparent or weakly scattering biological sample. The complication of this is that typically if you look into literatures for this kind of techniques, typically people relies on interferometry, which is much more complicated. So whereas we just use an LED array and take this data and trying to invert it. So at the high level, you need to solve for phase retrieval plus inverse scattering 3D reconstruction problem. So like I said at the beginning, typically once you build this setup, you need to find out this A matrix or this Fuller model. So I'm not going to be able to go through every single detail, but just give you a flavor of the kind of things we do for this instrument. So for example, we have illumination light going through the samples. So then we do some approximations. So one type of approximation was firstborn approximation or weakly scattering. So then you discrete a sample into a whole bunch of 2D slices. But bear in mind, our goal is to recover the 3D. Okay. So then we do some math. Okay, so I'm going to skip through all of these details just to say that once you do these assumptions, you can use standard assumptions in firstborn approximation and find out some very neat tricks. So in the end, what you find is that this model predicts there are two primary circles that are coming from the weak scattering of the object, plus some background from this background, which we will ignore. So then if you look at the actual intensity and the split spectra, you can see that it matches quite well. You can see these two circles on the real measurements. So then once we do that, we remove the backgrounds, we neglect the larger circle, and then we come up with a linear model. So which means that actually the problem is not that bad. Once we have a linear model, you can solve it by the standard deconvolution. So physically speaking, this corresponding to something like this. So you have absorption and phase from the 3D object. And we have these transfer functions in the Fourier space. So you can solve everything very efficiently. So then we just do a direct deconvolution. We can solve for absorption phase independently at different depths. So Z is marked with the depths. So the first instrument we demonstrated, here's some examples. So this darker contrast marked by PHC, this is a standard phase contrast microscope. So these are some cell clusters. You can see what you typically see under a cell phase contrast microscope. And these blue, red, this kind of jet color map are the quantitative reconstructed result from our measurement. So what I really like is this example. So zoom onto these cell clusters. So you can see a few cells that are clustered around. So in PHC, what we do is we need to physically move the objective lens so that we can see various different cell features. So this is a physical movement process. Whereas in our case, we simply scan through different illumination angles, then digitally reconstruct at different depths. So in other words, there is no physical scanning. And you can see that qualitatively they match really well. We can resolve all these subcellular features. Okay, so that's sort of the Gen 1. So that also lays out some foundational understanding of what what we call intensity diffraction tomography, or IDT, stands for. So then I'm going to quickly flash through a few recent developments in my group with the goal of pushing two things, I guess a few things. So in general, we want to build a very simple system. So this is in this kind of diagram, you're going to see various different systems are highlighting various different things. System complexity or system design, this is quite simple. We just, LED array. Computational complexity, I mentioned, is a linear deconvolution. It's very simple. Reconstruction quality is also quite good. But the problem with the first problem we want to tackle is that in the Gen 1 system, it requires taking almost 500 images. So it takes a while to capture that. So if you look at this, this is one of the data we wanted to capture. This is live C. elegans without any anesthesia. So you can see that as we scan through, the things will move around. So clearly we cannot resolve. It's as taking a single data set, right? So clearly we cannot resolve this kind of dynamics. The question is, how do we do this? How do we push the speed? So we come up with two solutions. The first solution is using exactly the same hardware. So what we do is we design acquisition strategies. So the acquisition strategy now involves turning on multiple LEDs. So this is the diagram we have. So we call this multiplexed intensity diffraction tomography, meaning that we're turning on multiple LED at a time. So graphically speaking, or in real life, this is what's happening in life. So we're turning on 4 to 8 LEDs, depending on different strategies. But in principle, the idea is that because if we're turning on a single LED, we have a linear model. If we're turning on multiple of those, because of linearity, the linear model still stays the same. So in principle, we can just solve slightly more complicated inverse problem and solve for the underlying object. The benefit of doing this is now things become much more fast because we're turning on multiple LEDs at a time. So this allows us to look for more dynamic process. So the example in this example, we imaged a live C. elegans embryos, and this is at 4 Hertz volume rate. Okay, so for each volume, remember that we need to take several images, but taking everything into account, each frame you're looking at is a volume, and it's 4 Hertz. And so you can see that. So in this XZ cross section, so you can see that subcellular features can be resolved in 3D, and they're in dynamic motions. So my student Alex also did some tracking of single bacteria in cells, and on the right you can see their trajectory that can be tracked using this device. Okay, so this is a multiplex technique. It turns out that if you're into this kind of computational imaging problems, so a classical result is to say that when you do multiplexing, you're giving up SNR. Okay, so that's one of the problems we're going to hope to tackle in the future. But so at the same time, we realized that actually we could also achieve higher acquisition speed using a much simpler hardware. So now we're talking about different microscope. That's not important. The more important thing is that now we've changed to a different LED ring. So this is the actual illuminator, but in reality, when we take the data, we just scan through each LED at a time around the rings. So the design principle is that if we place the LED ring at a particular distance h by design, such that the illumination angle matches with the NA of the objective lens. So then you can show that you can actually, so this is in the XY plane, so in the lateral spatial frequency domain. You can use very few LEDs, but while still capture majority of the 3D information you want in 3D. So this allows us to potentially push for 10 Hertz, more than 10 Hertz frame rate, volume rate, using as few as 8 LEDs. So it just turns out that this particular hardware design is particularly efficient for this kind of task. So just to show you some raw data and convince you this does work. So this is on a static cell sample on cheek cells with native bacteria over there. So this is the raw data. So in this particular case, we scan through every single LED. So on this ring, we have 24. Okay. So on the right, this is a full spectrum group. So if you still recall this explanation of the theory, you can see these two circles are rotating around, just to show you that this works. So then on the right, this is the reconstruction. So again, all these reconstruction are scan free. So we just scan through this 24 LEDs, run our algorithms, and digitally looking at different planes. And these Z planes we can select however we want. So we just selected a few planes. You can see that we can clearly resolve these native bacteria on the cells. So now from the technology perspective, this opens up for us to do dynamic imaging. So this is a live C. elegans. So now we can look at this at the real speed. Okay? So this is captured at 10 Hertz volume rate. So the C. elegans was happily staying at its living chamber in this particular case. So we can resolve all these subcellular features within its body. Okay, so in this instrument, we can get around 0.5 micron lateral resolution, axial resolution, 3 microns. But there's still some limitations. Okay, so if you look at this trade space, where marked here, there are some things that we still need to improve. Primarily, reconstruction quality and object complexity are not at the ideal extreme case. The reason is that fundamentally we're using an approximation, so weak object approximation or firstborn approximation. So in this particular case, what that means is if you look at some kind of synthetic object we're doing here, so it looks simple, but what we do is to change the contrast of this object. The higher the contrast is, it means that it has more scattering. So when the scattering becomes stronger, that means this kind of weak object approximation breaks down because the object intrinsically becomes stronger. Okay? So quantitatively in this simulation, of course, we can do this and quantify that. You can see that this accuracy is going down. Okay. So so the question is, how do we overcome this? So practically, so what you can do is to give up the computational complexity to derive a more complex algorithm, but it's much more accurate. Okay? So as a whole community, there have been a lot of developments to look into this thing so-called multiple scattering forward models and its corresponding inverse problem. And collectively, we have shown that this is very valuable if we look for higher quality or higher fidelity 3D constructions in complex objects. So the particular, so we have developed several different algorithms. So the particular one I'm going to highlight here is very recent. It just published. It's in press in Optics Express. So the algorithm known as split-step non-paraxial beam propagation method, SSNP. So the key feature is that this particular SSNP model is good for high NA system. It means that it is good for high resolution applications. And my student Jabe, who have done extensive work on GPU optimization and various different high performance computings. So he had actually made this code very, very efficient. So although when I show you in the next slide, it sounds complicated, but if you go onto our open source website and play with it, you will realize that it's not that big of a deal. Okay, so we have done, not only we introduced this forward model, but also shared very efficient implementation of this scheme to perform this kind of task. Okay, so how this works. So conceptually speaking, this is what you do. So you have a 3D object marked by refractive index Ri distribution. We discretize this into different slices. So in this community, a lot of people call this multi-slice approximation. So we take this into multiple different slices. So then you take this slice, instead of treating them as independent slices, which is the case in weak scattering or firstborn approximation. Instead, we consider the interslice interactions. So we do, conceptually speaking, is you propagate, you interact locally with the slice, and you repeat the process. So propagate, interact, interaction. So this interaction basically is of scattering. So you repeat this over and over again. So as you can imagine, the more slices you get, the more multiple scattering phenomena have been gathered in this computational process. Hence, the process become more accurate. And rigorous proof is given by the literature we have cited, and also our own proof. What's special about this SSMP model is that it takes not only into account of the direct wave itself, but also its axial derivative. So in this illustration, it's just a sketch, but in reality, we also take into account of the derivatives of the field, which means that you can account for some very bizarre situations at high NA. Okay, so just to skip all the details, just directly jump into the result. So we apply this model into the same data set I have shown you earlier. So this is exactly the same live C. elegans data I've shown earlier. So the firstborn approximation, a firstborn reconstruction shown here, this is the same reconstruction you have seen earlier, but just displaying on this particular color bar for easier comparison. So now switching to the SSMP reconstruction, if you look back and forth, what you can see is that a lot of these the subcellular features inside the C. elegans body gets much more enhanced. So in general, this is we have been observed using several different algorithms. So in particular, this means that these multiple scattering models allows us to capture these features which would otherwise easier to miss using single scattering approximation. So of course we can do this, apply it to this entire live data set. And also, although like I mentioned that the forward model looks complicated, but we can implement it very efficiently using GPUs. So this is not too of a daunting task. Okay, so we can do this on the live C. elegans as well. So the nice thing about this particular algorithms, although I didn't go into too much details, I highly recommend to read the details into this. So so in reality, when we build this algorithm in the reconstructions, we actually consider both the sequential, we call it sequential model when we're turning on one LED at a time, and this kind of multiplex model into a single holistic framework. So what that means is when you do the reconstructions, you can also correspondingly derive a single algorithm, regardless whether it's sequential measurement or multiplex measurements. And you can show that by using the method so-called auto differentiation. You can easily write one algorithm and just have extra flag or extra bifurcations to distinguish two cases. Just to highlight this capability, same algorithm, you're welcome to play with it, go to our GitHub site. What you realize is that we can also apply this to the multiplex measurement. So this is the C. elegans embryo data set I highlighted previously. So if you zoom onto particular features, what you notice is that some of these features in high resolution features become fuzzy and not very high resolution. But now using our SSMP reconstruction, you can see that there's some enhancement because of this kind of multiple scattering model. So again, you can apply this to the live data set. So here again, it's the same video, but now processed by the improved SSMP model. All right, so let me just quickly summarize. So this computation, in general, we call this field as computational 3D phase microscopy. We're trying to build various different hardwares, although same principle, but we do various different tricks to improve that, as you can see in the two setups I highlighted, and different forward modeling algorithms, forward modeling tools, and corresponding algorithms, with the goal of achieving various different attractive imaging capabilities, including system complexity, simple algorithms, high speed, handling complex objects, multiple scattering, like tissues virtually, and with high reconstruction quality. So here's just a flash through of various things you have seen earlier. So before I end this section of my talk, I just say that, like I said, many of our stuff is open source. So this is the general site you can go on to. So this is just, if you search my name, and you will find my group's website, and this will be there will be a link for open source. So everything will be there. And in particular, we had this fun project in collaboration with Benedict, who lead this very famous UC2 open source microscopy project. Benedict was actually a visiting student in my group for several months. We had a lot of fun discussions among various different things. So one thing he did is to actually translate the annular illumination IDT. So using this LED rings and translate that everything into the using the UC2 modules. So you can see that there's a mini LED over here, LED ring over here. Take some data. This is raw data he did on the cheek cells. So in the bottom, this is a reconstruction using our algorithm. So you can see that using this kind of very simple educational grades, you can still perform this kind of computational microscopy task in 3D. All right, so now let me switching gears next. I'm also gonna show you next projects around the theme of computational neuroimaging. So similar to the previous project, the project I'm gonna show you ended up being using very simple optics. In fact, many of those can be 3D printed. And also the optics we use are also very simple. I'll give you some more details later. And with the eventual goal, we can put this on a running mouse, okay, for a neuroimaging application. Okay, so just to give you some background, why do we do this? Okay, so the device we built we call it Computational Miniature Mesoscope, short for CM square. I might use the acronym during this part of the talk. So the whole point of CM square is to provide innovations upon this phenomenon research group community called Miniscopes. So for those of you who don't know, Miniscope is a miniaturized fluorescence microscope that had been originally designed for neuroscience applications. So on the right, this shows a breakdown of a standard Miniscope. So what you can see is that if you're from an optics perspective, if you use the same beamline as a tabletop fluorescent wide field microscope, so you have the objective lens and you have the excitation filter, dichroic mirror, etc. So the thing that it was great. So Miniscope had tremendous success in the application of neuroscience. So there are a lot of different studies have been performed. I welcome you to look into this review article in Nature Methods to get more details of this. So the point of this is that so the Miniscope have been developed for several years. So over the years, collectively as a community, we realized that there are still some limitations. So primarily the main limitation from the Miniscope is the optical design. So in particular, the optical design limits the field of views one can image. So the reason is because when we miniaturize, so when the community miniaturize the Miniscopes, the objective lens has to be a green lens at that time. So the green lens stands for gradient refractive index lens. If you have used this, you realize that it basically is a rod. It's a plastic or glass rod, and it's tiny. And at this the version you typically use in Miniscopes can provide field of views less than 1 millimeter square. Okay, so but a lot of studies have been suggested that it will be much nicer if we can build a Miniscope, so still miniaturized, but can provide much larger field of view. So there have been some attempts recently indeed. So you can see that these are very recent publications, 2021. One is called Widescope. This is built by one of my colleagues at Boston University. There is from the same UCLA group that started this open source Miniscope project called Miniscope-LFOV, basically means large field of view. So if you look at these kind of designs, you can see that they all use these compound lenses. The green lens can no longer be used. So then they can get to around 3x4 field of views, 3x4 millimeter field of views, while still maintaining the cellular resolution. There's some other designs to further scaling this up. You can get 8x10 field of views, but the resolution becomes much worse. It's greater than 39 microns. But it put into context, typically, if you talk about cellular resolution, the resolution needs to be less than 10 microns or even better than 5 microns. So overall, so the story is that if you look into these existing designs, although one can increase the field of view, but one has to sacrifice the system complexity. So these wide field compound lens designs can be very complex. Hence, they become very heavy. So I'm not marking here, but if you look into the details, they become much heavier. So it's not desirable. Or you have to sacrifice resolution. So put everything into context. All these numbers I show at you just to show you a picture of in the context of mouse brain imaging. What does this mean? At least in terms of the field of view. So these small circles, these are the typical field of views one can be captured by the miniscopes. The rectangular circles are these wide field scopes. But if a lot of studies, we wanted to enable brain-wide neural circuits understandings. So that means we wanted to look at the entire cortex. This is on the left. This is actual study have been performed on a tabletop system. So this gives you an idea. So this is our goal. So we want to build a miniaturized device that overcome all the existing challenges using CM2 while providing cortex-wide field of view while still maintaining cellular resolution. So it turns out this is not quite simple. So I'm gonna just highlight one particular challenge so that you understand why we perform the particular design I'm gonna introduce earlier. So I said we need to increase the field of view. So it turns out the reason a lot of the existing device becomes so complicated using this compound lens is that across the whole cortex, spanning around 1 centimeter square field of views, the cortex is also curved, and the curvature actually introduced around 1 millimeter depth range. So this is a real data reported in this paper. So in the same paper, they also made the observation that if you just use a standard macro lens that are designed to this specific field of view, of course, these macro lenses have already been performed using extensive lens design optimizations. So if you look at the central field of view, region A, you can resolve subcellular single neuron activities. But if you look at the peripheral region, region B, you can see that you can kind of make out where the neurons are, but they blurred out because of defocus and other olfactory aberrations. So it just highlights if you wanted to perform this kind of brain-wide capture, we also needs to take into this factor into account, so-called cortical curvature. So indeed, this inspired two particular groups, aim with the same goal, and so they have built these two tabletop systems. One is known as Rush, and the other is known as Cosmos. So essentially, if you I'm not going into the details, but if you look at the high level, how they think about the problem, basically they use a few lenses. Over here, this is an array of lenses. Over here, there's 2 lenses and a few cameras. So essentially, the idea is that in order to compensate for the cortical curvatures, you need multiple lenses to look at different depths so that you can compensate for the curvature while still maintaining high resolution. So that's kind of the idea that have been proposed in these tabletop systems. So our goal is basically so the system we built, CM2, essentially are inspired by all these prior work. Okay, so also a relatively longer background. Just hopefully you can appreciate the kind of designs I'm going to talk about in the next 20 minutes. So basically, our goal is to get 1 centimeter square field of view, sufficiently capture the entire mouse cortex, a 3D imaging capability. So again, this is because we need a device to compensate for the 1 millimeter depth range. And in addition, we want it to be wearable. So in this context for mouse imaging, the whole device needs to be less than 4 grams and also be of small size. So we're not quite there yet, but I'm gonna just walk you through some recent developments we have been doing, going through two generations, V1 and V2. Okay. So overall, this is a computational imaging device. So in particular, we're combining miniaturized optics and some particular computational algorithms to achieve this kind of capability. So different from the previous project. So just to highlight that, in the previous project, we were talking about face imaging. So these are coherent models, whereas here, since we're talking about neuroimaging, typically in particular case, we're dealing with eventual goal is to capture calcium activities. So we're talking about fluorescent imaging. So I'm going to talk a little bit about for model we're going to work with. So we see that they're slightly different because of the underlying difference in the image formation process. Okay, so jumping on to V1. So this device, because it's a standalone wearable fluorescent device, so it has 2 parts. One is for capturing the image, so it's imaging component, and the other is for excitation or illumination. So everything we build in the same module. So the first part, for this part of the talk, I'm going to just focus on the imaging and then come back to this excitation, which is also a non-trivial task. So for the imaging part, as illustrated over here, what we use is actually a very simple microlens array. So it's 3 by 3, and we use an off-the-shelf, very simple plastic molded microlens array. Literally, the cost for this microlens array is less than $1. It's very cheap and simple to make. So basically we assemble the microlens array along with excitation filters into this 3D printed housings, and then snatch it onto the CMOS sensor. So that's it. Okay. So then once we have that, we need to perform the following task to get the final reconstruction. So this is a general pipeline we performed for the CM square. So imagine you have some 3D fluorescent distribution, we want to image, we take some data, the data looks like this. So all of them look similar. So the characteristic is that we have 3 by 3 views. Okay, so this is coming from the 3 by 3 microlens array. So then, so these microlenses intrinsically capture the 3D information, but in order to utilize that, we need to do some calibration of the PSF. So these are the 3D PSF from one particular device. So then once we have the measurement and this 3D PSF, we can build a 4 model. So then once we have a 4 model, we perform 3D deconvolution to recover the 3D fluorescent distribution. Okay, so just to walk you through a little bit more details of the designs. So like I said, we have 3 by 3 microlens array. So the way you think about it is that we partition the single pixel arrays into positions. So each view is thinking about these positional information. And an outer axis, you can think about we have 3 by 3 angular information. So this angular information provides you the depth information. So put into a little bit more details. So this is also the process we use for capturing the points of functions. So also explain where the depth information comes from. So imagine you have 2 point sources. One is closer to the MLA, microresonance array. The other is further away. So now the corresponding points of function in the experiments we capture is look like this is what it looks like. So you can see that when it's getting closer, the off-axis force actually push away. Okay? So this you can easily convince yourself using a standard geometric optics. Okay? So this basically is, so basically because of these kind of depth variations of the point source, that gives you the depth Q, allows you to perform post-hoc 3D reconstruction. So in reality, this is a 4 model we built. So we are talking about 3D volume, but in the 3D volume, just like previously, we discretized the 3D volume into a bunch of 2D slices. These are a bunch of 2D slices. We have n slices. Each slice is denoted by xi. Okay. So then, in this particular Gen 1 model, we use this thing called depth-wise linear shift invariant model. That means for each slice, the slice is convolved with the same points of function. So the points function does not change laterally, but only change along axially. So the corresponding 2D measurement, which is a single shot, is basically a summation of this depth-wise convolution. Okay, so we convolve them slice by slice, then sum them. We get a 2D measurement. This is kind of a simplified version. You can get into more details from our publication to get more details. So in principle, once you set up this 4 model, you can solve the inverse problem. Of course, the challenge is that we're talking about 3D unknown and 2D measurement. So this is highly mismatched between the number of unknowns and the measurement. So reconstruction actually takes a bit of thought how to do that. So I'm skipping that part of the details, okay? But in principle, you can do this, and we can do this fairly well with sparse objects. So for example, for this resolution target, so this resolution target is tilted by some angles. This is the corresponding 2D measurement. Now running our 3D deconvolution algorithm. So on the left, this movie shows the depth-wise reconstructions. On the right, this is projecting everything into a 2D plane. So you can see that we can resolve this tilted plane and also resolve features around 7 microns. Now onto a volumetric object. So these are 10 micron fluorescent beads. So just to highlight the field of view we get, this is a 10x 0.25 objective lens and 2x 0.1 NA objective lens in Nikon's tabletop systems. The field of view we got is almost as comparable to a 2x objective. So in a single shot, we can recover these 3D location of the beads. And if you look at the corresponding elongations, we get around 200 micron elongations. So it's not great, but it does provide proof of concept to show that this kind of device can achieve 3D reconstruction capability. And in the Gen 2, we actually significantly improved this, which I will give you some idea how we do that. So one last example before I move on to Gen 2. So we put some fluorescent fibers on this curved surface. So this surface is actually 3D printed to mimic the brain surface. So then this is the maximum intensity projection of the reconstruction. So these depth-wise reconstruction is actually more telling of what we're constructing. On the top is our slice-wise reconstruction. At the bottom is a wide field measurement at the corresponding depths. So what you notice is that in the typical wide field fluorescent measurements, you have a lot of this out of focus stuff, right? But because in our reconstruction, we're only looking for the in focus features. So you can see that all of these out of focus blurs have been computationally removed. So this is one of the features we can get by solving this kind of deconvolution problem. You can think about this kind of like a computational optical sectioning. All right, so that's V1. So now I'll move on to V2 and then come back to some of the few points that I kind of skimmed through, but now getting into a little bit more details. So in V2, we're trying to overcome several challenges. So the first challenge is actually onboard excitation. So it turns out when you build this kind of miniaturized device, the excitation is not simple to build. So in V1 device, this is kind of a two-scale illustration of how we do this. We use off-axis excitation lights from LEDs. We have 4 of these, and then just use a 3D printed apertures to direct the light to the region of interest we want to image. It turns out this is highly inefficient. The primary reason, among many other things, is that the LED is a surface-mounted LED, the Lambertian source. If we do not add any collimating optics, this is not very efficient. So in V2, the most important improvement at the excitation side is we added this 3D printed freeform collimator. So how do we? So by doing this, plus a few other things, but the primary contributing factor is this freeform collimator. So we can improve the efficiency from less than 24% to over 80%. So this is going into a little bit details. I thought this is pretty cool. So everything was 3D printed on a tabletop lab quality 3D printer. So what we do is we design this in DMax. So then they just 3D print in transparent resin. So then everything is assembled into this illumination unit, consists of the surface-mounted LED, this illuminator, excitation filter, and this 3D housing. We have 4 of these, so this is a fully assembled device. So that provides our illumination. So if you look at the actual testing result, so this is the real excited light on a fluorescent test charge. So you can see that we can illuminate 8mm circular region with almost uniform excitation with this kind of design. Again, with very high efficiency. So that's on the illumination side, and also some cool, 3D print low-cost solutions to provide this kind of application. So now on the imaging side, so this is the data I didn't show in the first part, but was from the V1. Okay, so one of the things I mentioned was that the system is 3 by 3 microlens array. It's actually not as simple as it sounds. In reality, what you realize is that when you build this kind of device, we just have a 3 by 3 microlens array, nothing in between the microlens array and the sensor. So what you see is that at the central field of view, you have a 3 by 3. Okay, so these are the single view. This dotted line just to aid for visual inspection of the data. In the center, we do have 3 by 3 full size, but at outer field of view, some region we have 2 by 3, some region we have 3 by 2. At extreme corners, we have 2 by 2. And also, if you zoom in into these features, you will see that there are all these off-axis aberrations coming from comas, astigma, this and that. So you can compound all of these into this so-called correlation map. This is one way in our community to look at how variant these 2D PSF is in a 2D plane. So you can see that in the central region, this is the 1, which means that they don't change that much, but towards the off-axis regions, so you can see that the correlation degrade quite a bit. So in a nutshell, so we are actually dealing with a linear shift variant system, whereas in the V1 model, we made the approximation that this is invariant. But this approximation hurts us. Okay, so in the lateral resolution, which means that in the central region and moving to the outer regions, the lateral resolution degrades slightly, not too much, but in the axial resolution, it degrades quite a bit, from 140 to 190. Okay. So the other thing is that I didn't go into the details, but it turns out for this kind of fluorescent 3D convolution problem from 2D to 3D, for the kind of skills we're looking at, it's actually a huge computational cost. So for each of the 3D frame, we're talking about 2 hours computation, taking around 150 gigabyte RAMs. Okay, so we would like to overcome these issues. So the solution we come up with is deep learning. Okay, so more details is in this paper, but just say that this network called CM2net has a modular design. Okay, so it has 3 parts. One is view demixing net, essentially splits this 3 by 3 views into its own. So then we perform some kind of light field inspired reconstruction. One is essentially doing the light field refocusing and then doing enhancement. The other is doing view synthesis. So I'm not going into too much details on these networks. Just to say that this modular design, actually, we did extensive ablation studies and showed that this kind of modular design works really, really well, okay, for this kind of application. But one thing I do want to highlight is this lateral aberrations I just mentioned previously. So now you can see, hopefully you can see all these aberrations This is the real calibration data in the lateral planes. So the question is, how do we also encapsulate these lateral, these aberration information into the network? Okay, so that's the key. So step one is actually, we wanted to build an efficient forward model to capture these. So in this volume, we want to image 8 millimeter by 8 millimeter lateral, 1 millimeter in depth. Is too large to extensively capture every single point we want to image, because remember that our goal is to capture subcellular resolution. So laterally, that means give or take less than 10 micron steps, axially similar. So if we do that extensive PSF capturing, you end up with tens of millions of these points of function PSF measurement. So that's too much. So what we come up with is this low rank approximation. So the idea is that we have these sparsely physically measured PSF. So then we perform a low rank decomposition that says that this measurement, this PSF measurement, contains some basis PSF, which are invariant, with some coefficient which changes. Okay, so then we approximate the whole thing with K basis PSFs. So just to visualize these, this is top 5 PSF. Okay, so the first one, you can see that this is just nice 3x3 both sides. So then the rest of these become very funky. Okay, so that captures the variations in the lateral plane. We do this for the entire volume. The coefficient is 3D. These are calibrated coefficient is very sparse. The next step is because we wanted to do high resolution, we need to interpolate this. So this interpolation allows us to do high resolution 3D reconstruction. So we tested this on an unseen location. So this unseen location means that it's not in the calibration stat. So what you can see is that this is an interpolated result. This is the actual measurement. And if you look at the pixel-wise difference, they are very small. So now we build a new forward model. This forward model is much more complicated, but conceptually, it can be very easily explained. So we have is the object convolved with the corresponding basis PSF, but also remember that we have this coefficient. This coefficient tells you how much weight do you have for this corresponding basis PSF. So we repeat this for K times. Okay, so this is graphically, this is illustrate what the math means. And 3D object multiplied by the interpolated coefficient combined with the corresponding basis PSF. We have K of these, so we repeat this for K times. Then everything is summed. Finally, this summation over Z, same as the V1, we need to compound everything into the 2D measurement. So once we have that, that's our new forward model. So this works really well. So on the left top is our new model. So particularly if you look at the off-axis point, you can see all this aberration being captured. If we're using the previous model, you can see that they don't have any aberrations. So in the real measurement, of course, this is not a real same sample. We cannot do that, but qualitatively, you can see that indeed off-axis points at the outer field of view have a lot of aberration. So it's important to use this kind of LSV models to capture. So to put the story short, so essentially we use this forward model I just elaborated on and build a simulator. So the simulator means that we feed a whole bunch of fake objects, numerically go through this process and calculate the corresponding CM square measurement, and using the simulated data set to train a neural network, the CM2 net. Okay, once it's trained, then we apply to real experiments. Okay, of course we do some quantification. This you can find in our paper, but the important thing is it generalized to real measurements. So this is the one example. We have several in the paper presented. Just to show you that this works, and also a few key characteristics by doing this. So 10 micron beads. So this is a CM square reconstruction, and this is a 10x and 20x zoom ins. So you can see that we locate very well. So then the key thing we wanted to do for this is that we wanted to improve the axial resolution. So they see is that by doing this kind of LSV modeling and training a neural network, we can improve the axial resolution to less than 25 microns. What we started with what we call model-based reconstruction. This was from V1. is more than 185 micron in this particular device. Okay? So different device does have some variations. So this is a 8 times improvement in X resolution. And also because this is a feed-forward network inference, so then we can get more than 1,000 times faster reconstruction. So now this gets us to some real applications potentially later. All right, so that's everything I wanted to share with you with the CM square. Let me just say that we are working on the wearable version. So the big picture I just mentioned, the backend story does apply. We have been trying something, but with the interest of time, I'm gonna just skip this part, okay? All right, so let me just quickly summarize, and then we'll, basically I talked about 2 projects in my group that are working on. There's 2 different kind of quality of interest. One is phase imaging. These are for label-free microscopy. So the other project is for fluorescent imaging on a miniaturized device. The commonality is that we use very simple optics. Potentially they can be miniaturized or making it very low cost. And then we develop various different algorithms, either model-based or deep learning method to augment their imaging capability. So with that, let me acknowledge my group and many of my collaborators in various different projects and my funding. I'll be happy to take questions.
Thank you very much, Dr. Tian, for all those information. And I see also that we have many references where to check more details if we need to. So thank you very much for that.
Yeah.
So maybe I can kick it off with one question. I'm curious. So are you planning to control these 4 LEDs in the computational miniature mesoscope? Are you planning to control the 4 LEDs independently in order to generate illumination diversity? It's a basic form of structured illumination that could be further helpful in the image reconstruction. So have you made any plans for that?
Yeah, excellent. Yeah, excellent question. Actually, Vicente is reading my mind. So we are working on that. So the tricky. So in principle, we have an idea that we want to alternating these LEDs to create structural illuminations. So for those of you who work in this field, you know that for in vivo fluorescent imaging, structural illumination is very useful to reject autofocus backgrounds. So that potentially can improve both resolution and the visibility of the data. The challenge is right now is more on the engineering side because we're using LEDs. We have a collimator, but the spatial coherence is not great. So all of these means that if you just directly put some patterns in front of the LEDs, and when the pattern reaches the working distance we're working with for this particular designs, everything blurred out. Okay? So you don't see patterns anymore. So we are basically trying to figure out how to maintain the high contrast features at the brain surface. So this is still a work in progress. This is also confounded by the fact that we're going from 45 degrees, so it's a little bit tricky. But we're certainly looking into solutions like that.
Great. And if there's any other question from the audience, please raise your hand and we can probably address it. Otherwise, we will be finishing shortly in the interest of time.
Yeah, but if I can jump in, really fascinating talk. Thank you very much. I mean, you've definitely blown my mind with the results that you're getting on all these different works that you presented. It's really incredible, the kind of quality and speed that you managed to achieve.
Thank you.
I'm interested in everything, basically, but I'm going to just, in the interest of time, ask something about the first part. And this is also on a particular application. So with Pierre, for example, we're trying to put together a little computational microscope for pollen imaging in honey, basically to determine which kind of flower origin the honey comes from. And you've really inspired me to rediscuss if we can actually get a 3D reconstruction, which also would really be very helpful. But we definitely need this high resolution reconstruction, so we need less than a micrometer resolution. and yeah, the depth is good, and a large field of view helps us to use sort of really relatively simple mechanics for scanning the object also. But I was just wondering, so you used mainly low refractive index contrast samples, and in the end you showed a reconstruction for higher contrast samples, but they were not absorbing, right? What happens when you have slightly absorbing objects? Is that a real problem? And also, yeah, and maybe also you can comment on the scale of the LED matrix that you need. So you got really good results on the ring also, which has very few LEDs. So that's really impressive. But a lot of people use just 8x8 LEDs, and I think we have, or even 5x5 or so. We have a slightly bigger one than most, but yours is really large. So that's the second part of the question.
Right. Yeah. So I mean, comment on a few things. One is that about the absorption. So it's not necessarily in the order, but just jump onto whatever comes into my mind. One is about absorption. So in principle, the algorithm, so by the way, this is also all in open source, but feel free to email me if you need guidance on how to implement this. So the algorithm itself spits out both intensity and phase. So in one of our testing, we actually, I believe in this 2018 paper, I believe we imaged a one stain sample and highlighted that in the reconstruction, indeed, we can separate the stained part and unstained part. I think that was on one of the algae samples. They have this natural greenish stainings. So if you think about pollen versus algae, maybe they are comparable. I don't know, but that's my rough guess.
No, and I think it's similar. I was just wondering if it affects the other planes too much and therefore invalidates the model, but it works. Okay, that's pretty good.
In principle, it works. Okay, so so this is for the simple model. So, and also the other thing you mentioned about this resolution versus complexity. Let me just to clarify that. So the first one model we use, it's very simple. I highly recommend to use that for initial prototyping. So our general observation is that for small scale samples, it always works. It's just that when it comes to samples like C. elegans, the structure becomes more complicated. Some of the small feature might get lost. But if you flip back and forth between the simple and fast algorithm versus more advanced algorithms, you can see that the accentuation are just on specific region of interest. So it does provide sample-dependent enhancement. So typically we start with this first one of the constructions. Then we use this more advanced algorithm if it's needed. But again, all of these are in my open source website, so you can try both of them. It's just that their runtime is still different. First one basically is real time, on MATLAB or Python. This one I say is fast, but it still takes a few minutes, just because intrinsically we are doing different computations. So that's that. So then complexity of the LEDs. So the first version we built, this is definitely overkill, because this is a in total I think we have more than 1,000 LEDs. So this is an off-the-shelf Adafruit LED when we started the project. Then later we did our own circuitry just because of timing and various control had some issues with the commercial ones. So we had to build our own for this large matrix. So then we realized that this is actually not very optimum. So we switched to this one. This one is a 24 LED, still from Adafruit. So if you don't know about Adafruit, just search. So it's kind of like a hobbyist maker's website. This one is this is one actually when if you look into this LED array microscope literatures, some of the 2D technique I didn't have time to talk about. For example, 2D phase imaging one particular one known as differential phase contrast have drawn tremendous interest. So we did some initial development, and many other groups have done that. That one sometimes requires an array. For this ring, it still works, but the contrast may not be optimized. So for that reason, a lot of groups still prefers the kind of dense arrays versus a single ring. But if you look, if you look at the Benedict version, he uses, I forgot whether it's identical one or even smaller ring. So I guess all I'm saying is that the technology itself is scalable. It really depends on how small the platform you want to fit it in. One of my colleague friends who were also a developer in Caltech's group, he just showed me this setup with 8x8 array matrix and can do a lot of cool stuff like differential phase contrast, IDT, in his miniaturized device, very low cost for educational purposes. So I guess all in all, you know, it's definitely there are a lot of possibilities out there, and it's very simple. It's very simple to try it out, and the algorithm, I promise, is very simple to use. This is why we can, you can easily translate to UC2.
Thank you very much.
Yes, excellent. Thanks a lot for all those informations. Very interesting. And yes, as Tobias was saying, we'll probably be trying to replicate some of those techniques in our institute. Great. So thank you very much. I want to thank Lei Tian, our speaker, and everyone who is listening now or later. And see you next time.